Alright, so I have a ruler in front of me. Let me demonstrate the stable, unstable, and neutral equilibrium. So what is stable equilibrium? Stable equilibrium is when the fixed point is above the center of gravity. The center of gravity is in the middle. So when I displace the ruler, it's going to go back to the stable equilibrium position. Welcome back to episode number 4 of our lecture series. So in this chapter, we will be covering everything ranging from your moments to the principal moments to how you can actually apply the concepts that are taught here to the individual questions. So let's start off with understanding the key requirements of this chapter. Turning effects of forces. What is a turning effect? When you have an object here, let's say there's a seesaw, and we apply a force on one end of the seesaw, it's going to cause the seesaw to rotate in a certain direction with a certain speed. So we want to find a quantity that can effectively represent this turning effect. And that quantity that we have come up with is called moments. Moments comes with two characteristics. Number one, the direction of moments. Is it clockwise or anti-clockwise? Number two, for moments, we must also look at the reference point. So what do we mean by reference point? You cannot just say moments. You must say moments about a particular point. Let's say here we have, for this seesaw example, this is 20 newtons force applied on the right end. We would say moments due to the 20 newtons force about the pivot. Okay, a pivot is nothing more than just a fixed point. Let's formally define what moments is. Moments is defined as the product of the force and the perpendicular distance from the line of action of the force to the pivot. So the formula for moments is m equals to F times perpendicular distance. Now let's understand the definition. Force is simple. We are just going to take whatever the force is, whether it's 10 newtons, 20 newtons, or 30 newtons, multiplied by the perpendicular distance. Now this perpendicular distance is between 2 points. It is between the pivot and the line of action of the force. What is this line of action? Going back to this example, the line of action of the force of the 20 newtons is this extended line. Okay, it's an extended line that is parallel to the force and contains the force. So this is our perpendicular distance. Let's say it's 10 cm. In this same example, let's say we were to rotate the seesaw by a certain angle. Let's say the angle is over here. Okay. Okay, slightly. This distance is still 10 cm because that's the length of half of that plank. But the perpendicular distance will be different. Because if you apply a force of 20 newtons in this direction, then the line of action will be here. And the perpendicular distance from the line of action to the pivot will be this distance over here. Let me draw it in green color. So this is the new perpendicular distance that we are looking at. The key takeaway here is that the perpendicular distance can change depending on how you're positioning the force and depending on how much you're rotating the plank. Okay, this is just one example. We want to be using the same concept to many different scenarios. So that is moments. Okay, just take the force multiplied by the perpendicular distance from line of action of the force to the pivot. There's also another concept that's very important. That concept is called the principle of moments. A principle of moments is a principle that you must keep applying when you're solving any questions on this chapter. So what does it state? It states that when a body is in equilibrium, comma, the sum of clockwise moments must be equal to the sum of anti-clockwise moments. Let me add in a few more essential words. When a body is in equilibrium, the sum of clockwise moments about a pivot, these are essential, is equal to the sum of anti-clockwise moments about the same pivot. Two takeaways from here. Number one, we need the body to be in equilibrium in order for us to use this principle. Number two, the reference point that we are taking reference of must be the same point. You cannot have one point to be here and then another point somewhere else. It must be the same point. Let me give an example so that we can understand this a little bit better. You have a pivot, a seesaw over here. Okay, this is the pivot point. So this point must be fixed. If I tell you that this plank is not moving, straight away you must think that this plank must be in equilibrium. Because if it is not moving, then the net moment must be zero. And it must be in equilibrium. So if it is an equilibrium, then we can make use of the principle of moments, which states that the clockwise moment equals to the anti-clockwise moment. So let's say I have a force exerted down here. This force exerts what moment? It will exert a clockwise moment. How do I know whether it's clockwise or anti-clockwise? You just need to imagine that you have a plank, an actual plank, and try to imagine yourself pulling the plank down this way. It's going to cause the plank to rotate clockwise. So if the force will cause the plank to rotate clockwise, it means it's a clockwise moment. There need not be any actual physical movement, but it's about the thought. Okay? So this force will cause a clockwise moment, so this is clockwise. If the plank is in equilibrium, I know that there must be an anti-clockwise moment as well. So this is F2. And this is anti-clockwise moment. So the clockwise moment is equal to the anti-clockwise moment. Let's say the distance here, I don't know what this distance is. Let's say this is 10 and this one is 6. So since the clockwise must be equal to the anti-clockwise moment, and the moment is force times perpendicular distance, I can say that 6 times F2 must give me F times 10. This way, I will be able to solve for any unknowns, either the perpendicular distance or the force. Okay, so that is the principle of moments. We apply it to solve different questions. There's a common question where they ask you to identify the perpendicular distance. So let's say you have a situation where a plank is lying on a pivot in this manner. What is the perpendicular distance that we should consider if, say, the force is here? All you need to do is to draw one extended line. This is the line of action of F, and identify the pivot, which is over here. Then this will be the perpendicular distance from the line of action of the force to the pivot. I hope this is clear. Moving on to the next concept on center of gravity. Now, center of gravity is the concept for anything that has mass. Anything have mass will have a center of gravity. So center of gravity of an object is an imaginary point where the entire weight of the object appears to act. Okay, let me highlight a few important points. Number one is imaginary. The point doesn't really exist. It's a theoretical concept. So if I have an object here, let's say I have my wallet over here. My wallet, whether it has a center of gravity or not, depends on how I see it. Okay, I can say that center of gravity doesn't exist. Okay, because it's imaginary. Or I can think of my wallet having an imaginary point, and that's the center of gravity. So you must understand that all these are theoretical concepts. The point itself doesn't really exist on the object. But having this theoretical concept will help us to solve questions. Will help us to understand the real world better. Okay, and it's the entire weight of the object. So instead of thinking, let's say I have a box here, instead of thinking that, okay, there is going to be force exerted on the box from here, 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 I'm consolidating all these forces as one and saying that, okay, we don't have to consider all of these small forces. We just have to consider one big force, which is W, and that's the weight of the entire object. So let me give you guys some questions on center of gravity. So let's say you have a solid circle over here. Okay, I'll give you 3 seconds to pause and think of where the center of gravity might be. Alright, the center of gravity will be here, right in the center. Because this object is uniform. Uniform means uniform density. Same density throughout. So, on average, the weight is roughly in the center. If the bottom side is heavier, then the center of gravity would more likely be lower, because there's more matter at the bottom and the weight will be found closer to the bottom. So if I were to draw a free body diagram, I will be drawing a force that originates from the center of gravity. That's what it means. Now, next object, this is a ring. So think about where the center of gravity of a ring might be. The other parts is uniform density, but in the middle it's hollow. So think about where the center of gravity might be. Okay, this center of gravity will be found in the middle as well. So it doesn't really matter whether the center of gravity lies inside or outside the object. It's an imaginary point and it can be anywhere, as long as it accurately represents the point where the entire weight of the object appears to act. Alright, last object. Let me draw something fancy. Okay, I'm just going to draw this irregularly shaped object. And you guys can let me know where the center of gravity is. Now, how do we do such questions? Try to identify where the bulk of the mass is found on this object. So let's say I want to identify, I'm going to break it down into 4 quadrants. Okay, which quadrant has most matter in it? Okay, definitely going to be quadrant number 1. Okay, there's a lot more matter found there. So quadrant 3 as well, there's a lot of matter found there. So I predict that the center of gravity could lie somewhere here. Okay, of course, this is my own prediction. The actual center of gravity might be different, but who knows? Okay, you can do an experiment to find out what the center of gravity is. Lastly, I want to go through the concept of stability. Stability is defined as the measure of an object's ability to return to its original position. There's 2 factors affecting stability. Number 1 is the base area. So the wider the base area, the more stable something is. Number 2 is the position of center of gravity. In general, the higher the center of gravity, the less stable it is. And the reverse is true, the lower the center of gravity, the more stable it is. Let me go through each factor in detail. What's base area? Now, let's say I have two objects. One is a table, one is a box. What object has a larger base area? Is it the table or is it the box? Okay, if you say that it's the box because there's greater area in contact with the ground, then you're wrong. Because base area is referring to the area of the base. And clearly, the base of the table is larger. Okay, base area does not consider any surface area of contact. It only cares about the area of the base, not the surface area that's in contact with the ground. The larger the base, the more stable an object is. Okay, position or center of gravity. If I have two objects with the exact same base area, then definitely the one that is having a higher center of gravity will be less stable. Why is that the case? So you must think of a situation. Let's say we have two boxes. Let's say these two objects have the exact same base area. We draw the center of gravity. So one center of gravity is here, and then the other one is over here. Now, if I rotate them by the same angle, one of them will fall over, one of them wouldn't. Let me show you. So I'm going to rotate them by the same angle, like this. Okay, I'm going to bring this to the ground, and this is the ground. The two objects have been rotated by the same angle, but look at what happens. Now, the weight is originating from the center of gravity. The pivot is over here, the point of contact with the ground. So look at the object on the left side. The weight produces an anti-clockwise moment. And this anti-clockwise moment causes the object to rotate anti-clockwise back to its equilibrium position. Okay, it will rotate back to its equilibrium position. So this is stable. Now for the new object, what happens is that the object will topple over because the weight produces a clockwise moment that causes the object to topple over. So now the new center of gravity is going to be lower than the higher center of gravity. So this is how the position of center of gravity can affect the stability. When rotated by the same angle, the less stable object will topple first. Alright, last but not least, final concept is on the equilibrium. There's three types of equilibrium. Number one, stable. Number two, unstable. And number three is the neutral equilibrium. So let me illustrate with an example using a ruler. So a ruler can demonstrate, we can demonstrate the three equilibriums using a ruler. Imagine you have a ruler and then you are placing you are fixing a point on the ruler using your two fingers. Let's say I'm putting my two fingers here, I'm fixing these 2 points. So the ruler can rotate freely. The center of gravity of the ruler will be found somewhere in the middle with the weight downwards. Now for this ruler, if I displace it slightly, what's going to happen is that the ruler will topple over. So this whole ruler will fall over. And the center of gravity will move to a lower position. Which means that this ruler is originally in an unstable equilibrium. Yes, it is in equilibrium because there's no moment about the pivot, but it is in an unstable equilibrium because it has the tendency to move to a position of lower CG when displaced. Then what is a stable equilibrium? A stable equilibrium would be this position that it falls to. So this position, if I displace the ruler slightly, let's say I rotate it anti-clockwise, look at what happens. The ruler will be in this position with the weight over here, downwards. And the weight will exert a clockwise moment about the pivot. So when I release the ruler from this displaced position, it will go back to its equilibrium position here. So this equilibrium position is our stable equilibrium. The ruler, when placed in this position, will be in stable equilibrium. If it is in the red position, it is in unstable equilibrium. So stable equilibrium has the tendency to remain in a state where the height of CG doesn't change. This is not the actual definition. It's just an intuitive understanding that you can have. Now, what about neutral equilibrium? Neutral equilibrium is when the center of gravity and the pivot is exactly at the same point. Think of your ruler, but now the pivot is over here and the center of gravity is here as well. When you displace the ruler will not move because the weight does not provide any moment about the pivot. Remember, moment is force times perpendicular distance. So if perpendicular distance is 0, then the moments will also be 0. And if the moment is 0, the ruler will not rotate by itself when you displace it. You rotate it, it will stay in the same exact position. So let me show you guys a demonstration before we end off today's video. Alright, so I have a ruler in front of me. Let me demonstrate the stable, unstable, and neutral equilibrium. So what is stable equilibrium? Stable equilibrium is when the fixed point is above the center of gravity. The center of gravity is in the middle. So when I displace the ruler, it's going to go back to the stable equilibrium position. For unstable equilibrium, is where the center of gravity is above the fixed point. So if I displace the ruler slightly, it drops. Let me do that again. Displace it slightly, it drops naturally. Neutral equilibrium is when the fixed point and the center of gravity is at the same position. So from here, if I displace the ruler, it will remain in that same position. It will not change. Can you guys see? It is in the exact same position. So that is how you can understand stable, neutral, and unstable equilibrium using a ruler. I hope this video has been helpful in helping you to understand turning effects of forces. If you would like to see more of such videos, consider subscribing to our channel, share this video with your friends, and we'll see you in the next one. Thank you.